Welcome to this lecture. I hope you are seeing Professor Arvind's lectures on various types of distributions, various types of random variables with different distributions. A few of them are very standard and come repeatedly in various situations. So, these are given some standard names and we call them as specific types of distributions or specific types of random variables or specific types of probability mass functions, PMFs. So, if you think about it, all of these things are referred to the same quantity, which is the same entity, which is the probability space and the distribution we are dealing with. So, the first example that Professor Arvind deals with and I will also deal with here is the Bernoulli distribution, okay, or the Bernoulli random variable or the Bernoulli probability mass function. Okay, so, these are three things which kind of refer to the same thing and we will use this kind of terminology interchangeably. Okay. So, this lecture is on standard distributions, examples of how standard distributions occur in many of our the experiments that we have been doing. We have been looking at a few experiments all the time, tossing a coin, throwing a die, picking a ball from an urn, throwing balls into bins, picking a card from a pack. And Professor Arvind has been talking about these standard distributions or PMFs, and we will see how those standard distributions arise in our simple experiments. Okay, so that is going to be this lecture. So, the first one that we will look at is examples of the Bernoulli PMF, Bernoulli distribution. Like I mentioned, I will use these three things interchangeably in some sense. Hopefully, you see the distinction between these things and the fact that they refer to the same thing in some sense. Okay. So, the distribution is the entire thing, the random variable, the values it takes, the probability with which it takes them. The random variable of course refers to the variable itself, and the PMF is the probability. Okay. Together they make the distribution, that is the way to think of it. The Bernoulli PMF for random variable, if you say x is Bernoulli, there is a parameter p. Okay. So, what is this parameter? It is some number between 0 and 1. Okay. P is some number between 0 and 1, and when you say x is a Bernoulli random variable, you have to also say what p is. So, p could be a half is the most popular value, but you can also have other values, maybe half is a fair value in some sense, but of course, you can also have other values 0.1, 0.9, 0.999 or 0 or 1, anything is possible. So, when I say x is Bernoulli random variable, what do I mean? X takes values in this set 0, 1. Okay. So, x takes only two values 0 or 1, success or failure or however you think of it, but 0 and 1 in the random variable description, and the probability of 1 is p, probability of 0 is 1 minus p. So, you remember the way I write distributions, right. So, particularly discrete distributions, I would say x, the random variable, belongs to this particular set and indicate the probability on top of the value. Okay. So, it is a very convenient way to write probability distributions. Okay. So, this is the random variable which is Bernoulli. It takes the value 0 with probability 1 minus p and takes the value 1 with probability p. Couple of things to check whenever somebody gives you a distribution is that the total probability of everything should add to 1. Okay. So, that is the first thing to check. The other thing to check is each probability should be between 0 and 1. Okay. You cannot have both these conditions violated. So, you should check. So, 0 has probability 1 minus p, that is between 0 and 1. 1 has probability p, that is between 0 and 1. So, 1 minus p and p together, if you add them, you get 1. So, this is a valid PMF. So, this is the Bernoulli distribution. So, what are our examples? If you look at the first example and toss a coin, it is a very natural example. If you toss a coin, so you could say heads is 1 and tails is 0. Okay. So, you just think of a mapping like that, and your outcome simply becomes the random variable. Okay. So, x x refers to the outcome of the toss, that is clearly Bernoulli. Okay. So, x is Bernoulli with half probability, right. So, probability of heads is half, probability of tails is half. Like I said, you have to do the simple mapping of heads to 1 and tails to 0, that does not change the distribution in any significant way. So, tossing a coin is an obvious example. The other example, if you throw a die, okay. So, you can ask a question, is the number 1 Okay, so this could be one question you can ask. So the answer to this question could be the result of a random variable. So you could say x is equal to 1 if the number is 1, 0 otherwise. Okay, so what am I doing here? I am throwing a die and I am looking at the number that came out. Okay, if the number that came out is 1, I am thinking of it as success or something, and I am assigning 1 to the random variable x. If the number that came out is anything other than 1, 2, 3, 4, 5 or 6, I am going to assign a value 0 to the random variable x. Okay, so I have a 2 valued random variable, and that is clearly Bernoulli again. Okay, so now clearly you can see that this x here is Bernoulli, and what is the parameter? The parameter is the probability that I get a 1 when I throw the die, that is 1 by 6. Okay, so this is a different Bernoulli distribution. It is not 1 by 2, it is 1 by 6. Okay, so you can also look at another example, draw a card from a pack. Okay, and you can ask the question, is the card a spade? Okay, so once again I can assign x is equal to 1 if a card is spade and 0 otherwise. Okay, and you can see that if I do that, this x becomes Bernoulli, and what is the probability of 1? It is 1 by 4. Okay, so that is the Bernoulli distribution when you draw a card from a pack of cards. So in fact, you can also do something else here. I gave a number 1, so you can ask one more question, which is, I will put it as 2. So, so you can ask, is the number even? Okay, so when you throw a die, you can ask a question, is the number you got even or not? Okay, so even is what? 2, 4 and 6 are even, 1, 3 and 5 are odd. So if you think about it, is the number even is actually a Bernoulli distribution with the probability half, right. So 3 by 6 is the probability that the number is even, so that is 1 by 2. Okay. So this is these are a few examples of Bernoulli distribution and different parameters and how they show up in our standard examples that we have seen so far. Hopefully this is clear. Okay. So Bernoulli is a simple example, okay, in some sense. The second distribution that Professor Arvind talks about is binomial distribution. This is a very, very important distribution as well. Okay, or binomial PMF or binomial random variable, all of these are the same. So if you say x is binomial, you need two parameters now, a parameter n and a parameter p. Okay. So what is n? N is a positive integer. Okay. Usually positive, I mean you could say n is 0 as well. So let me just not say positive, I will say non-negative integer. By the way, what is the difference between positive and non-negative? Positive does not include 0, okay, positive will mean 1, 2, 3, so on. Non-negative means 0 is also included, so 0, 1, 2, 3. So n is could be 0, 1, 2, 3 like that, okay, any one of these guys, okay. And what is p? P is my probability indicator, so that is just 0 less than p less than 1. So it is some number between 0 and 1, okay. So for every such n and p, I have a binomial random variable which can be defined. So what is this binomial random variable? So it takes values, it could take n plus 1 values, it could be 0, it could be 1, it could be 2, it could be 3, it could be so on till it could also be some arbitrary value I in the middle, and then it could also be n. Okay, so it takes values from 0 to n, integer values from 0 to n, okay, 0, 1, 2, 3, 4, so on till 1. Okay. This I here is some arbitrary integer between 0 and 1, just to show how the probabilities work out. Okay. So the values that x takes when it has a binomial distribution is easy to write down. Now what about probabilities? Okay. The probability, it turns out, works like this. Okay. So we need this notation NC1, NCI, which have been also denoting n choose I. this is n factorial by I factorial times n minus I factorial. What is the meaning of this number? Number of ways of choosing I objects from a set of n objects. Okay. So, this is the combinatorial sort of formula, n choose I which is n factorial by I factorial times n minus I factorial, number of ways of choosing I objects from a set of n objects. Now, this n choose I will play a role in the definition of probability here. It turns out for probability that x equals I is actually n choose I p power I 1 minus p power n minus I. Okay. So, this is the probability. So, if you put I equals 0, okay, if I put I equals 0, n choose 0 is actually 1, p power 0 is also 1. So, you will simply have 1 minus p power n. Okay, that is the probability that a binomial random variable takes the value 0. And then you have the probability that binomial random variable takes the value 1, it is n choose 1 p times 1 minus p power n minus 1. And then you have 2 n choose 2 p squared times 1 minus p power n minus 2. And then you have 3 which is n choose 3 p cubed 1 minus p power n minus 3. Okay, so, this is for 1, this is for 2, this is for 3 and that is for I, and all the way to n. If you go to n, you have n choose n p power n 1 minus p power n minus n, that actually evaluates to p power n. Okay. So, this is the binomial random variable. It has a connection with the Bernoulli random variable. In fact, if you repeat the Bernoulli experiment n times independently and identically, the number of successes you have, number of ones you have is actually binomial distributed. Okay, so, that is the relationship anyway. So, that is important to see as well. Okay. So, now remember this I am claiming is a valid PMF, right. So, what is the condition for this to be a valid PMF? Every probability should be between 0 and 1, okay, and then all the probabilities should add up to 1. In fact, if you think about it, if I can show every probability here is positive, right. So, that is okay, every probability here is positive, that is easy to see, right, there is no negative going on, 1 minus p is also positive. So, everything is positive and choose I is also positive. So, every probability here is positive, non negative, and then if I show that they add up to 1, okay, that is enough, they have to be less than 1, right. So, all of them are positive and a bunch of positive numbers are adding up to 1, which means each number is also less than 1. So, that is enough to convince yourself that these probabilities will actually add to 1. If you show that they add to 1, then you are done. Okay. So, how do you show something like this adds to 1? It turns out you have to use this binomial expansion formula. It is very important that you know this, a plus b to the power n. Okay. So, some of the standard formulae you learn growing up is a plus b squared. You also learn a plus b cubed, okay. Maybe some of you will learn a plus b power 4 also. So, all these are standard formulae that you learn. Now, there is an extension to all that formula, a plus b to the power n, for n being any integer 1, 2, 3, 4, 100 whatever, okay. And that formula is the following, this is equal to summation I equals 0 to n choose I, a power I, b power n minus I. Okay. So, this is the main big formula. You can show, for instance, if you put n equals 2, you will get your familiar a squared plus 2ab plus b squared. Okay. So, anything you put n equals 3, if you put you will get a cubed plus 3ab squared plus 3a squared b plus b cubed. Okay. So, you will get all those things as special cases of this formula. This is the master formula for a plus b power n. Okay. So, this is the most important thing here, which brings everything together in the binomial for the binomial distribution. So, here this is true for any a and b. So, you can put a equals p, 1 minus p and b equals p. Okay. If you do that, what happens to the left hand side? You get here 1 minus p plus p whole raised to the power n equals summation I equals 0 to n choose I p power I 1 minus p power n minus I. Now, what is this guy? 1 minus p plus p and p will cancel. So, you get 1 itself. So, this is just equal to 1. Okay. So, this shows that all these probabilities n choose I p power I 1 minus p power n minus I I going from 0 to n, if you add up all the probabilities, you get 1. Okay, all of them are positive or non-negative and they add up to 1, which means this is a valid probability mass function. Okay, so this formula for binomial expansion is important to know, and it appears in so many forms in probability calculations again and again. Okay, so it's good to know this n choose I very well, in some sense what happens to it and all that, and these kind of summations involving binomial coefficients and the binomial expansion form is important to know in many calculations in probability. Okay. So, this is the binomial distribution. So, let me take a few examples of this and show you how it will look. If you, the simplest case is binomial of 0 comma p. Okay. So, what is 0 comma p? Whatever p you pick, but if n is 0, what will happen? This is just in this case, this x, which is binomial 0 p, will simply take just one value 0. Okay. So, if it just takes one value, the probability of that has to be 1. You think about how you put it in. So, this one value, it takes probability 1, it is not at all interesting. Or you might want to take binomial of 1 comma p. So, in this case x takes values 0 1, and if you put in your formula correctly, you will simply get 1 minus p p. Okay. So, this is actually Bernoulli, right. Binomial of 1 comma p is Bernoulli, it is not at all interesting, it is you do not get a new random variable if you do it. So, it starts to get interesting if you put binomial of 2 comma p. Okay. So, you would get 0 1 2. Okay. So, this you will see is 1 minus p squared, this one is 2 p times 1 minus p, this one is p squared. Okay. So, this is the binomial of 2 comma p. So, likewise you can do. So, let me do just at least binomial of 3 comma p, and after that I will stop. I will let you visualize what happens in the general case. 0 1 2 3. Okay, 0 is 1 minus p power 3, 1 is 3 times p 1 minus p squared, 2 is again 3 times p squared times 1 minus p, this guy is p power 3. Okay, so, these are all the way in which you evaluate the binomial coefficient. So, maybe I will show you just one more example, binomial of 4 comma p. So, in which case x takes values 0 1 2 3 4. 0 is with probability 1 minus p power 4, this is 4 times p into 1 minus p cubed, 6 times p squared into 1 minus p squared. 4 choose 2 is 6. Okay. So, how did I get 6 here? For instance, 4 choose 2 is 4 factorial by 2 factorial into 2 factorial, that is 6. You can evaluate it. Likewise, how did I get 4 here? 4 choose 1, you can see is actually 1. Okay. 4 factorial by 1 factorial into 3 factorial. Okay, I am using the same formula, I am not doing some magic here. You just use the same formula, you get the answer. Okay. So, this will be again 4 times p cubed into 1 minus p, this is p power 4. Okay. So, this is an example, this is how the binomial random variable will look, okay, if you look at different cases. Okay. So, that is the example. So, I am going to see some situations in which a binomial random variable comes. So, if you look at the first example, toss a coin n times. Okay. And I set the random variable x to be number of heads. Okay. So, it turns out if you look at this number of heads, the number of heads could be 0 or it could be 1, it could be 2, so on till n. Okay. So, the values that the x random variable takes number of heads is from 0 to n. Now, what is the probability that x equals I? The number of heads is I. Okay. The heads could occur in any one of I positions chosen from n positions. So, you will have n choose I, then the number of heads has to be half, right. So, I am sorry, half power I times number of tails, which is half power n minus I. So, you get this probability also. So, clearly from this we see that x is binomial with n and half. Okay. So, you toss a coin n times, the number of heads is going to be binomial with n comma half. Okay. So, hopefully you see this method of how I got this probability that x equals I. If you have I heads, okay, you have to count the number of possible ways in which I heads can appear. Okay. So, that is a little bit, so that is where the n choose I comes about, and then you have a 2 power n in the denominator. Okay. So, this is just, I mean, this is just n choose I divided by 2 power n, right. Okay. So, 2 power n is the total number of possibilities for n tosses. I have done this before, and what is n choose I? Number of possibilities with exactly I heads. This is total number of outcomes. Maybe I should write outcomes here. We have seen this before. So, the n choose I by 2 power n. 2 power n I can write as half power I into half power n minus I. So, this comes into that familiar binomial form. So, you have x being binomial with parameter n and a half. Okay. So, number of heads that you get when you toss the coin n times is a binomial random variable. Okay. So, I can now repeat this same sort of experiment with, so anytime you repeat a Bernoulli experiment n times independently, you get a binomial distribution. So, for instance, you throw a die n times, okay, and you let x be the number of ones. Okay. Once again, this takes values 0, 1, 2, 3 to n, and probability of x being I. Okay, now is a little bit more confusing. So, we can't maybe do this in such a simple fashion. So, now so you have to think about the calculation a little bit more, but you can argue that this will be n choose I into 1 by 6 power I times 5 by 6 power n minus I. Okay. So, how do you write this down? So, for instance, the total number of possibility is 6 power n. Okay. So, when you throw out dice n times, you have 6 power n. Now, how many possibilities, how many outcomes have exactly I ones? The I ones could occur in any one of the any I of the n position, n throws. You have n throws, any I of the throws can be 1. So, you have n choose I possibilities times. Okay. So, for the I guys, you have just 1 power I, right. So, 1 has to occur. For the I positions, there is no choice. For the remaining positions, you have, it could be any one of the 5 possibilities. What are the remaining 5 guys? 2, 3, 4, 5, 6. Okay. Any one of the 5 could be there. Okay. Hopefully, you see that you have n throw of the dice. Okay. There are I positions with 1, remaining positions have other than 1. Okay. So, how many ways in which you can choose these I positions? N choose I. The I positions themselves have just one possibility. All the remaining positions other than have to have other than 1, right. Other than 1, how many possibilities are there? That is 5 possibilities, 5 power n minus I. So, that is the same as this guy. So, this clearly shows that x is binomial with parameter n and 1 by 6. Same thing with drawing the cards, but when you do the repeat the experiment IID, you have to draw the card with replacement. Okay. So, that is the next thing I want to show. If you have draw a card n times with replacement. Okay. This with replacement is very crucial, otherwise you will not get binomial. Okay. And you let x be the number of spades. Once again, this x also belongs to 0, 1, 2, 3 to n, and once again with a careful calculation you can show probability that x equals I is n choose I, 1 by 4 probability of spades in the I position, and 3 by 4 which is probability of non-spades in the remaining positions. Okay. So, this will show that x is binomial with n and 1 by 4. Okay. So, this is an useful factor. Remember, if you have a Bernoulli distribution, you repeat it n times independently and count the total number of successes, you always get a binomial distribution. Okay. So, this is an important fact, and we have just shown this by experiment. N IID repetition of Bernoulli P, okay, and you let us set x as the number of successes. Okay, Bernoulli is either failure or success. Success refers to 1, failure refers to 0. So, the number of success or ones. Okay. Then x is binomial with n comma p. So, this is a very important fact, and we have verified this with quite a few examples. Okay. So, that is the binomial distribution. The next important type of distribution that we will consider is this geometric distribution. Okay. So, quite often in many examples and real life situations, you may not be concerned with the total number of things that sometimes occurs. You might want to know the first time an event will occur, a success will occur. Okay. So, you start the experiment, you keep repeating it. What is the first time that success will occur? Okay. So, if you do that, you end up getting what is called a geometric distribution. Okay. So, let me define the geometric PMF once again. So, the geometric PMF has just one parameter p. Okay. It does not have multiple parameters, just p. It takes values. So, there are two ways in which people write geometric PMF. Sometimes they start at 1, some people start at 0. So, I am going to start at 1, so on. I mean, there is no end here. Okay. So, x, this is the first step of random variable which is not finite. Okay. Bernoulli is finite, as in it takes only 2 values, 0 or 1. Binomial is also finite, it takes only n values, n is a finite number. Geometric can take any large number as its value. Okay. It could be 1000, 10,000, 100,000, whatever. There is no limit to the maximum value that a geometric random variable could possibly take. Okay. So, 1, 2, 3, so on. Okay. Set of all natural numbers. Okay. And what is the probability that x equals I, some number here. So, I is some arbitrary number here. Turns out this is 1 minus p power I minus 1 times p. Okay. So, that is the probability that we assign. Okay. Remember, what is my distribution? Distribution is two things: all the values that the random variable can take and the probability with which it takes that value. So, what are the values the geometric distribution is going to take? 1, 2, 3, so on. Okay. What is the probability that the random variable takes a particular value I? It is 1 minus p power I minus 1 times p. So, once again this value is non-negative, it is between 0 and 1, it is greater than or equal to 0, and we have to check whether all these numbers add up to 1, right. So, remember what is the probability we will write here. So, now if you write the probabilities on top of these guy, this will be just p, this will be 1 minus p times p, this will be 1 minus p squared times p, so on till what will be this? This will be 1 minus p power I minus 1 times p, and so on. Okay. So, this is the probability of a geometric random variable. So, for instance, if you take p equals half, okay. So, x takes values 1, 2, 3, 4, so on. Probability of this is half, probability of 2 is 1 by 4, right. P equals half, if we put, you will get 1 by 4, this will be 1 by 8, this will be 1 by 16, so on. Okay. The probability keeps on dropping very fast. Okay. So, you can also take p equals 1 by 3, let us say, in which case x will be 1, 2, 3, 4, so on. Okay. Probability of 1 is 1 by 3. This guy is what? 2 by 3 times 1 by 3. So, you have 2 by 9. What about 3? It is 2 by 3 squared times 1 by 3. So, it will be 4 by 27. What about 4? It is 2 by 3 power 3 times 1 by 3. So, you will have 8 by 81, so on. Okay. So, that is how the probability goes. Okay. So, for particular values of p, you can figure it out. Okay. So, do all the probabilities add up to 1? I have to check that, otherwise it will not be a valid PMF. So, let us try and do that. So, you have p times p plus 1 minus p times p plus 1 minus p squared times p plus so on till what is the ith term? 1 minus p power I minus 1 times p plus so on. Now, p appears as a common factor here, I can pull it out. I have 1 plus 1 minus p plus 1 minus p squared plus so on, right. The arbitrary term is 1 minus p power I minus 1, it does not matter. Okay. So, it goes on and on and on forever. Now, there is this result on geometric progressions. Okay, which says that 1 plus r squared plus r cubed plus so on is actually equal to 1 by 1 minus r if absolute value of r is less than 1. Okay, so, we will put 0, does not matter. Okay, if absolute value of r is less than 1, it should be strictly less than 1. So, if you have a summation like 1 plus r squared where r is strictly less than 1, r could be half or 1 by 3 or something, then this summation is 1 by 1 minus r. Okay. So, that is what it means. So, if you use this result of geometric progression, then the summation becomes p times 1 by what is r here, 1 minus p, and I know this 1 minus p is absolute value is less than 1. Okay. So, of course, so you have the situation, I mean, for instance, p equals 0 is a sort of a bad situation here, right. So, if p is 0, nothing will really work out. You can't, you have to have p being strictly positive in some sense. Okay. So, we will assume that. So, we will take p to be greater than 0, okay, between 0 and 1. Okay. So, we will take it like that. So, things work out well for us. So, it is 1 by 1 minus r. Okay. What is r? 1 minus p. Okay. So, you notice that this summation has r equals 1 minus p. So, you have p times 1 by 1 minus p, which is what? P times 1 by p. So, it will cancel and you will get 1. Okay. So, the summation works out to something that is correct. So, this is the geometric distribution. So, let us once again see some of our examples, and I think even Professor Arvind would have mentioned this example. If I toss a coin repeatedly, okay, and if you set x as first time index of, so toss a coin repeatedly, so you also have to number the tosses. Okay. So, you number the tosses as 1, 2, 3, so on. Okay. So, first toss, second toss, third toss, so on. Okay. So, the first toss, second toss, third toss and so on. The first time index of toss in which h occurs. Okay. So, this is the way in which geometric random variables will usually show up. Okay. So, you have 1, 2, 3, so on, the first time that h occurs. Okay. And you can quickly see probability that x equals I, that the first time head occurs in the ith toss is half power I minus 1 times the half. So, this means, so this usually means this what this means is tails occurs in first I minus 1 tosses, right. So, first time head occurs must be in the ith toss. So, in the first I minus 1 tosses you should get tails. So, that is the probability of half I minus 1, and here heads occurs in ith toss. Okay, that is another half. So, this is exactly this. Okay. So, you have half power I minus 1 times half. So, x is geometric with half. Okay. So, this is hopefully easy to see. And then a second example I will say is throw a die repeatedly. Okay. And again number the throws 1, 2, 3, so on. Okay. So, what is x going to be now? X is the number of the throw in which 1 occurs for the first time, right. So, this is the first, I am going to consider success. If 1 comes, that is a success, and the number of the throw in which 1 comes is this is going to be my geometric random variable. And here again, if you look at probability that x equal to I, you will get 5 by 6 power I minus 1 times 1 by 6. So, once again what is this? This is the probability that 1 does not occur in first I minus 1 throws, and then this is the probability that 1 occurs in ith throw. Okay, so, clearly we see that this x is geometric with parameter 1 by 6. Okay. So, you can again do the card experiment also. You can repeatedly keep drawing cards with replacement from a pack, and you will see the first occurrence of spades will be a geometric distribution with parameter 1 by 4. Okay. So, I am not writing it out in detail. So, but in general here is a fact. Okay. So, if we repeat a Bernoulli experiment independently and identically, okay, occurrence of first success becomes, okay, so I should say parameter p here. Okay, first success is geometric with parameter p. Okay, so this is a fact. In general, this is also true. Okay, so hopefully these examples gave you some simple real life situations where the geometric and the Bernoulli and binomial distributions occur, and so I think it is important to know these distributions very well, what kind of values they take, what probabilities with which they take them, and how to identify situations in which you can apply them. Okay. Thank you very much. That is the end of this lecture.